So we continue this line of questioning, and this time it's about fault tolerance. This whole topic of where is computing going, what do we actually need, and maybe let me start with a provocative question, like, is NISC dead?
No, I don't think so. I think it's kind of funny because there's kind of these kind of psychological elements of the field, in that for a long while there was NISC around, and the Lord had said, we shall do NISC, and then the Lord came on stage again and said, NISC is dead, and then NISC was kind of considered that, but I think for a long time NISC was kind of a bit overhyped, and now it's a bit underhyped in the sense that I don't think we are not at NISC yet, in the sense that full-scale experiments like the kicked rotor experiment by IBM, I think that's a full-scale NISC experiment that's extremely interesting, even though it was dequantized, but never mind. But kind of this is the full-scale NISC thing that we need, not just run some 3-qubit thing on some dirty body computer. I think that's still quite interesting. You have log depth, let me know this in very precise detail. I can talk for hours about this, but log is log. I mean, that gives you some room, and we should maybe also look for NISC++, a bit beyond NISC, and probably we'll talk about this more later.
What does NISC++ then look like? Or is this also something that Google would probably consider, or is Google like, is NISC dead for Google?
No, NISC is not dead for Google. We have these random circuit sampling. It's a useless application, but it is a proof that quantum computers can do something you can't do classically. And because that exists, it means there's not zero hope that even with the error rates we have, the connectivity we have, there couldn't be an application that could be done that was better. Now, we don't have that application right now, but there's good reason to believe that it's not impossible. Yeah. So we definitely have a team that looks for small-scale, basically harder than classical applications without error correction.
So you would both agree that there is still value in pursuing NISC and looking for applications there?
Of course.
Yes.
Yeah.
All right.
Obviously, if we can not wait 20 years for a fault-tolerant computer and get useful things done now, that's better for everyone.
All right, that leads me to the next question. What do we need to not have to wait 20 years? Like, what could the software community, you pitched some of that, but maybe Jens, you can also answer that. What do we need to get there faster than in 20 years?
You need an algorithm. So we are always trying to find good algorithms that run on small quantum computers. It's just we haven't found the one that is definitely going to run and it will actually outperform a classical algorithm.
Yeah, I mean, I tend to agree. I mean, first, as a kind of addition to the former point, there's also a bit of like an academia versus industry perspective. Like if you run a 293 people team, then of course you want to go on a yourself on a kind of ship that's really going in a different direction. In academia, you can also look here and there, which makes you a little bit more flexible. So sure, never mind. Then what do we need? I think we need everything, in the sense that so like the recent IBM success was largely driven by just better average gate fidelities. That sounds profane, but get the better gate fidelity help in getting under the threshold. Then we need better, well, you're here for better software, and Austin's beautiful talk has given you a bit of an impression on what that could be, and we still need more applications. I mean, recently I gave a talk in Switzerland, and it was kind of funny because I gave the talk, there were lots of questions, I said, oh, great talk, and then somebody said, yeah, that was a good talk, but that was practical. And he said this in a very negative way, what it really insulted, like, good talk, but practical. And I said, no, I mean, I think also good people should think about things that at least have a practical flavor. There's a bit of a cultural barrier that people think about very high-level questions and others don't go there. So I think there's room in the middle that we should and must explore.
Yeah, I would certainly second that. You know, I did 10 years in academia. I've now done 10 years in industry. Even when I was in academia, I was always looking for problems that were practical. And you can do that from a self-interested point of view. I mean, why would you want to work on something that has not had some forethought to say, will it lead to anything any day? Why would you want to burn years of your life on something that means nothing, right? So, you know, too many academics, I think, don't ask that question. Before they embark on years of effort, are those years of effort going to amount to anything? Because it shouldn't be enough that it amounts to a few papers and they get the next round of funding. That shouldn't be enough.
Yeah, well, I can only agree.
Yeah,
so practicality is definitely a huge aspect in all of this. And of course, theory is one part, and I think the error correction community and the fault-tolerant community is very heavy on theory, actually. But what do we actually need to turn some of that theory into practice, into practicality, and maybe also into software. You always read these fancy papers about new codes in theory, but when you then look it up, if there's software around to actually make use of that, sometimes it's tough to find anything.
Yes. Yeah, but I make a similar point. I think we should overcome some psychological and cultural barriers in the sense that high-level code design people are often interested in interesting math around code design and they're mathematically trained, but they don't want to go into the dirty realities of noise models or connectivity or something. That's really for lower beings. And then you have practitioners who work on the physics, the exciting physics of the problem, but then these cohomologies are a bit too fanciful. So I think we should look also in the middle, and there's some things that are happening. For example, very plainly, you have a code, and if you have very highly biased noise, you can do something about the code to kind of accommodate this. That seems simple, but it gives up the thresholds by far. Then there was this gross code on IBM that also kind of is an LPC code plus in a way that is also more physics non-agnostic. And we need to think more in this direction because I do think there's a lot of potential.
And in our case, well, we have the device that we need. We have the software. We need to explore fault tolerance. It has taken 10 years of Google-level funding and hundreds of people to get there, but that's the answer to what did we need to get that thing. But yeah, starting now, the last month, I can promise you the quantum error correction team at Google is very excited. We are running everything we can on the chip that we have, and we're just excited to see it grow and get better and better.
So that's of course an advantage of having a device. I was recently visiting the Google team. It was so funny because Patrick was showing me around, and then because we are, as a theorist, are never allowed to touch, but then Patrick came close to the fridge, and then the technician screamed, "Patrick, don't touch!"
Oh yeah, the Google lab is locked down.
Yeah.
Oh no. The Google lab has got, well, we worked out the following thing, that if you get too close and touch our hardware, it dies because of electrostatic shock. So you can literally blow up one of our chips by touching the fridge. So there are big cordons around, there's special electrostatic flooring, you have to wear special gear to even be allowed literally to touch our devices from 6 feet away, all right? So most of our workers at Google are not allowed in the Google lab anymore. It's become a very specialized place to work. You have to wear steel-caped boots. We have fridges that weigh many tons. They have forklifts going in there. Everyone just sort of stands around the mezzanine floor and just looks down at it in amazement. It's a wonderful place, but yeah, most people are not allowed in.
One question over here from Matthias.
Yeah, it's maybe more a question towards Jens because I guess Austin has a very strong opinion towards surface code. So you mentioned there are a lot of codes, and if I open, I don't know, quantum error correction, so I can get lost there for days. Do you have an opinion what kind of code will survive? Or is it just too early to say we should explore all fronts?
So it's funny because there were so many meetings recently. I've seen many people here the last weeks, and there was a hardware meeting just on the BMBF 2 days ago. And then the question, oh great, why don't we fund the architecture that's most sustainable, that will fly? Is it superconducting qubits, ions? Is it this or that? Then we just scrap the others and we fund the real thing. And Eisert says, I don't know. I give you a similar answer that I don't quite know because that will also depend again on the platform. I don't know, LPC codes are a beautiful thing, but they're maybe not so fanciful in the architecture that we are talking about. Superconducting devices and surface code go together quite well, very well. But in other architectures, like eye traps where there's no connectivity constraint, you can play different games. So, frankly, I don't know. As a theorist, it's a lecturer's position because you can think about basically all of them.
Yeah. And I would second that. Even when you have 2D square lattice non-nearest neighbor interactions, surface code is the best thing we have at the moment. But the color code, hexagonal color code, also maps exactly to that lattice. If you have a good enough decoder, in principle, you need half the qubits for the same code distance. And there's very active research to see if we can get that better code. And then everything will change. Right? And that's even in our hardware. And yeah, certainly Google is not just interested in superconducting qubits. We have some interest in the neutral atom platform. All bets off. It's not necessarily going to be surface code. It's still not a bad starting point. It has a very high threshold, but you have many, many other options.
Maybe jumping on that, on the hardware topic, which is the most promising technology? I mean, you're heavily invested in superconducting at the moment, of course, but there are so many other platforms that now show quite a lot of promise. Anything in particular?
I think the race is still very open. Yeah, I mean, in terms of the big ones, there are many people investing in superconducting techniques. They're very good because they are big, you can get the wiring in. It's an important point. A lot of people will say, hey, we want our qubits to be small, but not yet. If you only have hundreds of them, it's really nice to have them big because you can use large-scale tech to get your signals in. The neutral atoms are doing spectacular the last few years. The ion trap guys are doing spectacular. So, it's still a very, very open field. It would be really arrogant for anyone to say, hey, we're winning. No, it's a very interesting developing field.
Indeed, I would again agree in the sense that what is the most promising architecture is very non-constant in time. For example, cold atoms obviously have made a big splash from last November onwards, and now I was at the hardware meeting and everyone was talking about cold atomic architectures, and this might go away again. Also, the function dependence is different. Superconducting devices are like this. They all go better and better, and the average gauge fidelity become better and better. And then you talk to, you don't talk to them, right? Because they don't talk. But if you would talk to quantum people, I shared the office with one of the founders in the past. They would talk about their thing, but their functions are a step function. It could be the most scalable architecture, but it could be the biggest gigantic failure of mankind of not getting anywhere. This is recorded now. But this is a step function. But you have to try it. It's a courageous thing to do. It's a good thing.
Great.
Yeah. The competition keeps us on our toes. So
yeah,
it's good for everyone.
But there seems to be a lot of agreement between the two of you. Maybe let me try to ask you a question where the answers might differ. So if there would be one single piece of software that you could wish for that could be existing just now or just in a second, what would that be towards the success of quantum computing? And don't say a software that solves everything. That's not the question.
Well, maybe a fanciful decoder that's not just running for a memory experiment, but does compiling, decoding all in one go, and it's still local, and you can put on the fridge. Actually, I've been thinking about this myself a bit, a cellular automaton thing, where you do everything local, and you decode, and there's no computation, you put it on chip, and it runs the show, including computation. That would be fun.
And I would just refer back to my talk. I want a quantum compiler that outputs the right form of ZX graph. Yeah. Before next year.
That's a very particular request. So how do we get the people in the room involved in all of this?
You email me and we talk.
Yeah, same thing. We've done the three-colored version of the ZX, and feel delighted because that's a great playground. It's just one color more. It's one element of fun more. Play with it.
Google could put a big bag of money in the middle of it. Will motivate people.
They've done it before. It's not impossible.
From these third league German universities, it's a bit more difficult. But
yeah, our goal is to solve the problem open source style, so everyone has access to the solution. These things are hard problems. If Google did just do it internally, well, there's a chance it wouldn't get shared. Whereas if I insist that we do it as an open source project, which took some insisting, I might say, it's better for everyone in my mind.
Oh, I actually taking back my previous joke. Maybe I say something more meaningful, which I think, because now we are together, we are a little bit in too much agreement. I can see that, but I think that's also a good thing because I think this kind of separation of labor is still active, and for some time, at some point. The smart people were in academia. And then it changed. I remember at QRP, I was sitting at a table and they were all the Google, your boss, and they're all the CEOs of the big companies, and then Frankfurt Stratum myself. They were all making fun of us, the dinosaurs, I think it's still very constructive in that academia and industry are still together. For example, we have a paper coming out with you guys, 2 days from now or Monday on Hamiltonian learning, where we calibrated the Singapore chip for Google. And that was fun because it turned out that even Google had something to learn from us, and we had a lot to learn from Google. But I think neither academia nor the industry is gone, and that's something that we should make the best use of because we are still in the game and we should contribute together.
And maybe to give a specific example, Google just released a bunch of funding for transduction. So there's a question about how do we communicate from chip to chip. That's a very appropriate problem to work on in academia. It's a lot of physics, a lot of small-scale hardware development, and so that is not something we do internally. We encourage academic partners to do that.
All right. So, well, there's a lot of agreement between the two of you. Is there any disagreement in the audience? Like, any questions, anything?
It's not a disagreement, but like a question. So, coming from the algorithm side, like, do you think there should be more development or more work on like NIST algorithms or early fault-tolerant quantum algorithms? Because there seems to be not much development in the recent times.
Sure. I mean, people should certainly try. If you ask me personally as a researcher what the probability of success is, I will say it's low, but that's because I'm biased. I work on error correction. But it's definitely worth trying, as long as it's not me. But we all have our biases. No one's found that wonderful algorithm, but if someone does, it's so impactful on the field that it's definitely worth looking.
Are we supposed to be short answers? My answer is yes. But are we together in the Munich Quantum Valley? And like we met again, like how many seconds ago, like a week ago or something in Eisert, and they were talking about this in the sense that we presented like a constant depth learning algorithm that's NIST-like. It's a baby step. I think we need more of that, totally. And there's even an entire K within the Munich Quantum Valley dedicated to that, where we, by law, have to do something about this. And of course we are.
All right, there are two questions over there. Just shout if you can while I bring you the mic.
I think just a quick comment on the kind of, is it worth working like still on this NIST algorithm? And as a person that spent quite a bit of time working on them in the past, I think this is, like, to me it seems important just also like to remember that if you want to work on them, just like be smart about how to work on them, because there is, I think, there was like a lot of results and a lot of people working on those algorithms in like pretty naive way without like deep understanding.
Yeah.
And I think that was like a problem that we had in the community a couple of years ago, and I'm guilty of that. So like I'm saying that from experience. And I didn't spend enough time learning actually how this algorithm works. So I wasted kind of a bit of time on that. So I think like NIST algorithms, I think there's like personally like there's a lot of interesting things to explore, but just be intentional about it. And don't just try, hey, I will like solve another application with like VQE, but actually think why it's a good thing to explore, why it's worth it, what's the potential, and not just like think, I mean, maybe it will work, maybe it won't, because I think that could be a wasted effort.
Can I comment on that? Because I do think that's true. We should work on this, but in a clever way. Because indeed, as you say, or I say this even more strongly, in that sense that there were too many papers on 5 qubits, some variation algorithm, you make the plot and they say, I've solved the aviation problem, I've solved the schedule problem of whatever carrier and so on. That is, these days are over. Of course, you can still publish, but it's not interesting, yeah? But I think it's still interesting to, in a smart way, talk about this and see where the limits are, dequantize stuff, but also see what's on the other side.
And I would say another one, just people don't do enough research on what can be solved classically well. Right? Too many people say, here's my quantum algorithm, isn't it amazing? And they have not actually checked what can be done classically. You really want to engage with the classical experts. First, go contact a cloud service quantum chemistry department. They exist, right? People that actually do industrial chemical computations. Ask them what they can do. You'd be surprised what they can do, all right? Before you go and publish a paper that says you can do something better, check with the experts.
There's one question right over here, or a comment.
Yeah, I've got a question that's along similar lines, but perhaps that allows, similar to these reorientable gates, for you to pick an avenue to go down. So a lot of companies, including Quantum, you control all these things, they have fairly ambitious roadmaps that put large-scale fault-tolerant quantum computing in the next 3-4 years, right? And given the colossal amount of research that has gone into developing NIST algorithms for very little output, is it more appropriate to be pushing for the development of early small-scale FTQC algorithms rather than continuing development on NIST? And part of the answer can be like these roadmaps are wildly unrealistic, or anything like this. I wonder what your thoughts are on this.
Oh, my wife recently said, "Can you bring A to school?" And I said, "Who's A?" She said, "Alba, your single daughter." So that's how I'm with abbreviations. What is FTQ?
Fault-tolerant.
Oh, you see? I've proven my point. Good. No, we should do both. I mean, we've said it. We should do both. I mean, like the fault-tolerant computer means you kind of put everything on one aim, and this might happen, and it's a colossal effort, as we've seen. But even culturally, we need success before that, because we will not have the fault-tolerant quantum computer. I mean, Seth Lloyd gave the keynote talk at the meeting. I mean, I invited him, and he said a fault-tolerant computer will be there in 10 years plus minus infinity. To be fair to him, 10 years ago he said 20 years plus minus infinity, so that it is consistent. Yeah? But this is too long. We have to deliver something, and we have log depth, yeah? But go for it. I mean, random circuit sampling is like interesting scientifically and completely uninteresting practically. I'm not so negative that we can go beyond that. That's slightly more interesting practically and still interesting scientifically. I think we have to deliver this otherwise.
So is it unfair to interpret that as you believing that these roadmaps that show fault tolerance in 2, 3, 4 years as being unrealistic?
Oh, you have to ask them. I mean, there's also an interplay of funders and companies and so on. I'm not going there, but I mean, I'm rather optimistic about fault-tolerant computing. But that does not exclude us from thinking about things to do along the way.
I did just present a talk on a fault-tolerant quantum computer.
Yeah.
So they're still baby size, but if they exist, they'll get bigger. So the time starts now. It's not something you wait 10 years for. You know, we can do 4-logical qubit, proof of principle, fault-tolerant computer, quantum computation on a chip that really is below threshold, will get better as it gets bigger. So, you know, the time starts now. We just need to make them bigger now.
One or two more comments, questions before we wrap this up.
Yeah, this is for Jens. Actually, I think you just said it again. So you made this comment. NIST is log depth, which sounds right to me. But it also sounds like you're referring to kind of a specific result there. So I was wondering if you could kind of elaborate on what's the what kind of closes the book on the fact that NIST is only for log depth.
Okay, I'm not happy to say that, but I'll be short. I mean, there have been a couple of papers that basically said in poly-log depth, you're either close to the maximally mixed state in trace distance or in the Gibbs sample wall. What we did not long ago was you take an arbitrary local model, like non-unital, whatever, amplitude, you name it, a local model, and we can show that if you have a deeper circuit in a very precise sense, all you have is log depth, and you can as well take the stuff before and just throw it out, and it will not matter for the output. Again, in a precise sense, I'm happy to explain this thing more. So you have log depth, and whatever you add will not do anything. If you go beyond that, you're also in regimes of dequantization. That's what Austin also said. You have in many regimes a classical efficient algorithm in that to a certain level of precision solves the problem, and depending on your disclaimer, this will be efficient in 1 or 2 spatial dimensions. And you have no Baron plateaus, right? That problem goes away, but for the wrong reason, in that you're so little expressive, so that you're not really getting anywhere. So if you go beyond log depth, you are dying. But log is log n, right? I mean, that's it. I mean, you can run Shor's algorithm in log depth if you want. So let's see what we can do in log depth. It's not the end of the world, but there's a very, I'm happy to send you the reference. This log depth is really more or less set in stone, in a very tough stone.
Final question and comments? Go for it.
Question. Thank you very much for really valuable information. I'm very fan of these United Nations 17 SDGs, social development goals.
Thank you.
Which covers poverty, education, and so on, climate change, and so on. I would like to hear your views, naturally, when you talk about it, and maybe an advice for the this community, but also for the industry, right? So how we could embrace not only quantum computing per se, from R&D perspective, which I'm very, very fond of, but also thinking about use case. Right? So how eventually quantum computing could do lead it better world to others.
Okay, I have something to say. In the sense, you might be surprised to hear that I'm actually writing a kind of an article on quantum computing for climate change. Not as a research article, but more like a perspectives article. The background being that I give many public talks, and then I give a talk and say, yeah, that's very nice, but what we are actually interested in is climate change. And then I have a very close friend I studied with. Like we were a group of 5, and all 5 people became academics, funny enough. But they're all in different fields. I'm the only surviving physicist. One of them is a climate researcher. He gives public talks and said, oh, that's great. Cool stuff, climate. But what's really cool is quantum computing. So he's like annoyed. We met, like, I'm so annoyed. He said, oh, I'm so annoyed. So in the end, we sat down together and we are like, just compiling numbers with the help of Seth Lloyd a bit on HHR algorithms, or just counting numbers of how unrealistic that is. Oh, realistic. So give me like 6 more months and then I have something to say. It will not be hype. It will be painfully realistic. Extremely quickly.
Yeah, I just wanted on this point specifically because like in Montreal a month ago, Eleanor Ripple said something to answer this question, which was that she said like when she's talking with like some young researchers, students, she says that like if you want to solve climate change, go work somewhere else. If you want to explore new science and like just move the frontier of our understanding of the world forward, this is the right place. And I think that summarizes it pretty well.
Yeah, I would agree with that. I would push back on the idea that we need a quantum computer to solve climate change. We know what we need to do to solve climate change, but mostly we are not willing to do so.
Well, all right, let's conclude with that. Thanks for your insights. That was fun.